we're back for the nighttime live, albeit a little bit late. We got caught up in something, and now we are here. I'm just fixing up their snacks, and then we will get this live started, and we will look at this. So Baji gets his snacks separately. Sometimes I have him hunt his snacks, actually, because that gives him a little bit more exercise, and also lets the others finish their snacks, sort of without the aggression of having to compete too much. So we're doing a little bit of snack time here. Hi Ram Candy. We are a bit late today, but that's okay. Here we are. We're live. I'm gonna change their water. Oh gosh, Suji, your foot was in the water. I'm gonna do a little bit of fixing up of stuff around their food station, and then we will go over some Galaxy stuff, albeit it's a little late, but that's okay. We are here, and generally we are live far past this time, and we did do a live earlier this afternoon. Ram Candy, how are you doing? How is everybody? Welcome, welcome. Thank you for joining. Thank you for joining the live. Hello. Hi. Oh my gosh. Everybody is so cute here. The kitty cats and everyone. Thank you everybody for joining. Thank you if you're watching this as a live upload video later on. Welcome, welcome. So it has been very cold here in Boston, but here we are. Hello. Hello, here's Fuji, Suji, and Baji. Baji is drinking his water. I think we're gonna be over here tonight. So I'm gonna set up over here. If you wanna put your comments in the chat, feel free. We will read your chat messages. We will catch up with everybody. And we will cover some material on galaxies. I have some notes already on that, and we actually did some of it in this afternoon, but that's what's going on. Hello, welcome, welcome. Welcome to the live. We're gonna get started. I'm gonna rotate the camera in just a second, but for now, please do enjoy the view of the kitchen and some kitty cats, and I will be starting my astronomy live here soon. In fact, let me show you. Here's the book that we will be using, and we will be chatting with everybody and covering some material. Again, welcome everybody. Hello, Ram Candy. Hello, Chuckin. And thank you for liking the live. Yes, if we could get to 10 likes, that would be amazing. Yesterday, last night's live, we actually got to 50 likes, if you will. So that was quite something. And here is me. Here's my face. I'm the Baji, the Handsome Cats host, and I make the videos and Baji, Suji, and Fuji also join a lot of these videos, and I will be covering some galactic astronomy today. Galactic, galaxy astronomy. In fact, maybe I will put, I don't know, I haven't decided on the setup today. I was trying to see if I can be on the couch, but maybe not. Maybe not. Maybe not. Hi, Reese. Reese is here. Hello. Hello, hello. Okay. That light is on. This kitty cat is here. This kitty cat. Okay. Good morning, good night, good evening, everybody. Here's the kettle that the phone will be. Over here, you can see Baji's perch right there. Hello, everybody. I am gonna get my water. I'm gonna chat with you here soon. Oh, you can see Baji right there. Look at him. So you guys can catch up and get settled here, and we will start our live here shortly. How's it going, Reese? How are you doing? I wonder if it's gonna be a quiet one with the numbers, and that's fine. Maybe people will catch it later, so I'm still gonna cover the material that I want to cover. I realize I didn't really look at myself too hard in the mirror. I took a shower, and here's me. Live's a bit late today. Yeah, I got late. I was up to something important. And now here I am. I'm gonna like my life from the iPad. Okay. Okay. So, oh, thank you for liking the live. Thank you for liking the live. Can we get 10 likes? Can we? Can we get 10 likes? Oh my God, that reminds me, Reese, yesterday at the last night's live, did you know that somebody got so mad about the topic we were discussing because of that word? Somebody has been leaving me a ton of hate comments today, everywhere, on my shorts, like straight up harassing type of comments. And at first I responded more kindly, and I was like, oh, honey, are you sad? Like, are you okay? Because I thought, is it like just a kid who's really mad? Remember your story with the guy, the S word, the unalive word? That word and the jokes about the moon landing, or I don't know, I think it was mainly the fact that the vibe in the live was somehow threatening for them, and nobody was like paying. There was too much going on, and I guess like we didn't pay enough attention to this kid or guy or somebody who was getting so mad at us. And I thought I didn't realize that they were so affected. And so I was like, dude, somebody was talking about their own past experiences, and maybe that is helpful to them. So like, don't take it so personally, or it is a topic that, it is something that is pretty common. It's dark, but it's a common thing. So talking about it might help somebody, actually. But anyway, I know, but they were going just nuts in my comments. So I had to like block them. Lots and lots. Some of the most weird hate comments I've ever seen were left by them. So I'm like, okay, so you're so triggered because we said some word and that might have been hurtful, but here you are leaving the most hurtful comments on my stuff. And that's because I didn't defend him. I'm like, I didn't know I had to defend you. I didn't know that you were being, you were as offended as you are. I know. So I just wanted to tell you the story because there's not a lot of people here. So I thought, sure, I'll start with that. That there's, not only that, there's another crazy person who has been lately on my comments, and these two found each other. So like these people who are leaving these comments, they always find the other people too that are that are like that. So, and then he's like, you and your buddies were attacking me. Did we attack him? I don't know. I didn't realize, because a lot goes on in the chat. So anyway, I just hope people know that sometimes a lot is happening in the chat, and you might have to decide if the environment is right for you or not on your own, and the host, that is me, may not be able to babysit every single chat message. But yeah, anyway, welcome everybody. Thank you so much for being here. Thank you, thank you. I think we were not. We were just doing our regular thing. The regular live is a little bit rambunctious, you know. I think the live people were rambunctious. But I will say, hello, Mehrana. Hello from Iran. Hello to Iran. Welcome. Sometimes the live can be a little rambunctious, but the person who is hurt by the live said some of the most hurtful things possible to me today in a few different ways, in a few different comments, and even teamed up with another person who was being so awful and creepy to me in a comment. And then he replied to that comment saying more bad things to me, and tagged me. So it's not even like he's trying to make a friend with that other guy who's also bad or creepy. So he's like tagging me to make sure I see his comment. So anyway, I will say you've got my attention if you're seeing this, and I understand that maybe that was what you were lacking last night at the live. And I'm sorry, sometimes the lives have a lot of people putting stuff in the comments, and I might not be able to give you the attention you so needed last night in the chat. So anyway, sorry if somebody felt less than hello Mehrana Godam Kesavar Hested. I don't know if I said that right, but very nice. Thank you for being here. Oh, and Reese, I think like it's strange because it wasn't said in a way that that was, you know, I think there are certain words that you can't say on, for example, TikTok. But YouTube is a little different. YouTube is a little bit more, how should I put it? I think YouTube is more real, if you will. Like all kinds of real people, real world people watch YouTube for like the more, yeah. I know. Everybody's sense of humor is different though. So I get that. I get that that things are not funny to everyone. But that particular story with that particular thing in it was literally somebody's story. So what I have an issue with is that if somebody wants to share a story, then they should be able to. Ultimately, for that thing that we can't say to be less, we want people to feel less lonely and more included. So I don't know what about that was confusing to this person. But yeah. And then the comments they left me are the types of comments that also make people feel potentially lonely and bad about themselves, which would cause more of that thing that they had such an issue with us mentioning. But it happens all the time in the real world. So that's why I'm taking this time to speak about this, because I'm like, okay, we can't talk about it, but it does happen a lot. And the way you're acting hurts people. So what do you want from me again? Anyway, thank you guys for being here. I have to get some water. I'll be right back. Oh God. There we go. Reese, here's one of them. Reese, we have somebody special in the chat. Alright, so I am gonna fill some. I need to wash my water bottle. I'm gonna use a mug at this time to drink some water. I can't wait to see I can't wait to see. No. This is another guy. But this is a different one. Potentially also very problematic, but in a different way. You'll see. You'll see. I'm glad you're here, Maud, because you'll get to see the things that I've been dealing with, if that happens. Or maybe I'm wrong. Maybe this is not that person. Even I'm confused. Welcome to the live, everybody. Thank you for joining. Reese, I think I'm in the mood for shooting this shit today. I'm like, I don't know. I don't know if I can get it together. All day, I was dealing with some weird stuff on YouTube and I felt very, very, very introverted. And then I went live in the afternoon with like the lowest energy ever. So if you saw my live earlier, anybody, everybody, thank you so much. Politeness. Am I supposed to be polite to you? Do I owe that to you? Are you talking to me? I don't even know. So, then I took a nap and then I had a very good evening. So here we are. Here we are, and I'll get my notes. 1 second, please. One second. 1 second. Aw. Now there's less people. Maybe I've been impolite enough for the... Ooh. Ooh. And I'm already in my PJs, which I like. Reese, you're doing a really good job with the modding today. You're doing a really good job with the modding today, because look at you, you're writing all kinds of supportive messages and whatnot. I have water on the counter that I am making sure is not there anymore, so I could put my notes down. Whew. Okay. All right. Don't ask why I'm randomly laughing sometimes, okay? Just roll with it. Just roll with it. There is a guy I follow on YouTube who says this a lot. He says, just roll with it. Just roll with it. We have a laugh and a joke, but never want to be upsetting anyone. I think Doro would say otherwise. I think he wanted to upset that person a little bit, but at the same time, he didn't really do anything or say anything upsetting, so... you know. Okay, so remember how we talked about galaxies? Oh, boy. Reese! This is it. This is one of them. Look at that. Look at that. Look at that. He's not the same guy, but he has also felt very threatened lately. For absolutely no reason. Now you're witness. Sorry, I have to tell my mod to read the message because it won't show to the normal people. And I wanted someone else to see what I'm saying. Cracking me up, man. So the nucleus of our galaxy is the next topic we will talk about. We talked about our galaxy earlier this afternoon. I actually showed those pictures that I showed last night again today. I showed the examples of 2 different galaxies. One that we have an image of edge on, and one that we have an image of face on. And as you know, we are part of the Milky Way galaxy. Sometimes we call it the Milky Way galaxy. Sometimes we call it our galaxy. Or if we just say galaxy, it usually means the Milky Way galaxy. Hello, Joel. The mod is modding today, guys. So I forget. One second. Now I'm distracted. I need my other notes too. Um, so last night I showed you some pictures. One was an artist's impression of the Milky Way galaxy. Now you might ask why an artist's impression, but even though it's kind of an obvious thing, but I'll still explain. We are in the Milky Way galaxy, so we can't really take a picture of it very easily. We would have to leave the galaxy to see it edge on or face on or something like that. That's what I mean. We can take a picture of a part of it, but if we want a picture of the full galaxy, say edge on, face on, something like that, then that would be hard because we'd have to traverse a very long distance to get out of the galaxy and do that. So we generally only have artists' impressions of the Milky Way galaxy, which is our galaxy. Hi, Alamaru. Which is a spiral galaxy, and we learned a lot about the spiral arms and how this is a disk-dominated galaxy, so there is a ton of gas, clouds, stars. Certain arms or spiral arms have a lot of star formation activity going on. They are hotbeds for star formation. We will name some of these spiral arms as well in a bit here. But generally speaking, this type of spiral galaxy has some features, and it's always good to compare it to some other spiral galaxies that we can image either edge on or face on. And so we did that, and I'm going to find the page number for that real quick here. I have a notebook with certain things I write down to help me find things easier. Oh, here it is. Didn't have to look too hard this time. But basically, certain couple other examples, I just wanted to get the names correct. You don't have to even try to be cute. Oh, thank you. So certain other galaxies that are examples of spiral galaxies, which we can compare to, are the following. And I just want to make sure I get the names right. That's why I had to turn the page. They are NGC 891. This is a galaxy that we actually have an image of edge on, and I'll show it to you in just a second. And then we also have M83. So he's talking about me clearly. Yes, he's talking about yours. So M83, you might have heard the name of this galaxy. It's kind of commonly named as an example. And so I'll tell you in just a second about something similar to something along the lines of what you're asking, boss. Thank you for the question. But M83 is another galaxy example that we have an image of face on. And so these two images of spiral galaxies kind of tell us what sort of we might look like, Milky Way galaxy might look like, because these are also spiral galaxies with what we think are similar features. So our galaxy's total luminosity of 23 billion solar luminosities is fairly bright. So we are a fairly big so I believe boss is asking about the planets. I think that's something I'm not sure I know how many planets we have in our galaxy. So but I was going to answer the question in terms of the stars. How many stars do we have in our galaxy? That could be something that we have a better answer for, because as you will see in the discussion, we have how many stars? Oh, okay. Yes, we will have an estimate for that for you really soon here, boss, and it's an excellent question. So in terms of stars, you will see how we come up with sort of an estimate for how many stars and things like that, pretty much based on luminosity. So luminosity, we're really nothing compared to the universe. Yes, absolutely. So luminosity is something that we can measure, and based on that, and also based on the types of stars we think live in these spiral galaxies, whether it's the spiral arms or some other parts, the dust that we think there is, etc., we can actually make estimates of how many stars. So I will cover that, and you will see. So I'll show you the picture in just a second, but NGC 891 has a very prominent dust lane running down the middle of the galaxy, for example. And so these different parts, spiral arm versus dust lane, etc., will have different types of things. So Generally speaking, stars are supposed to obviously contribute a lot to the luminosity. So if you have a very bright galaxy, you can deduce some things about the number of star count and things like that, for example. And our galaxy, you should be proud. You should have a conversation with Neil deGrasse. Oh, well, he's probably too popular and too famous and busy at this point. But thank you for the suggestion. Ooh, can we get 10 likes? So, really quickly, something that we actually covered last night, but we can say it again. Our galaxy has three main components. These are a disk. We actually have what we call a thin disk as well as a thick disk. Also, we have something called a bulge. The bulge is something in the direction of Sagittarius, which is at the galactic center, actually. And the bulge is also mainly seen in radio waves. So another thing, yes, and then the last part, the last component of our galaxy is the halo. Very nice, Reese, he remembers. So basically, another thing to keep in mind also is that you're going to see different things in different wavelengths. So you might see the bulge in mainly radio waves, but then other things might be in X-rays, UV, or visible light. All of that will give you a different picture of the galaxy. Fun fact, for example, we found, never seen Star Wars, boss. I've seen some of the wait a minute. Star Wars, right? What am I thinking of? I think I've seen some of the Star Wars movies. Or maybe I haven't. Wait, is Star Wars the one with, I'm not big into sci-fi. I know. I talk about science, like pure science, but I'm not big into sci-fi, I'm sorry. So real talk, the Luke, I'm your father type thing. Oh, yes! I have seen that. I have seen that. I have seen Luke. I have seen some Luke stuff. So, oh yeah, they say some pretty... Is it Star Trek that says something like going above the speed of light? That's not possible. So, probably I don't like the sci-fi stuff too much because it does have some inaccurate statements about physics. I don't like when people say Mach whatever over the speed of light. That is misinformation. But I understand it might be a good entertainment source. So it's all good for the people who want to enjoy it. And if it inspires people to study space, then of course. So anyway, so the Galactic Center, going at the speed of light is only possible for photons, which is the particle that makes up light. So light goes at the speed of light, but nothing else can. You can go at a speed very close to the speed of light, but you cannot go at the speed of light unless you are light. And space and time are relative, but the speed of light is a constant. That is actually the basis of the special theory of relativity. Did I say that right? Did I say that right? Space and time are relative, but the speed of light is a fundamental constant of nature. Okay? So Sagittarius, or the Sagittarius system, there's different parts. At the galactic center is a big example of what we think hypothetically is a supermassive black hole, which is of course supposed to not let light escape, which means that it should be black, dark, all that stuff. Dark star is another name for it. But turns out it's very bright around Sagittarius system because the black hole Sagittarius A star is constantly eating more from its neighboring objects, and those things that are accreting and falling into the black hole end up being very bright radio sources, for example. So Things like that are fun facts about our galaxy that we have also discussed. Neutrons. Yes, so neutrinos, I think you mean neutrinos. So we've discussed so Reese is saying neutrinos are high energy particles can exceed the speed of light in a certain medium. So yes, so neutrinos are high energy particles can go at a speed greater than the speed of light in that particular medium. But the speed of light in vacuum, I should have said, is a constant in nature. Nothing can go at that speed unless it's light. Okay? That's okay. Yeah, so neutrinos are something that we study through their interaction in the Antarctic ice, for example. And part of that detection method is that it creates a particle shower, which then goes at a speed greater than the speed of light in that medium, which is ice. Nothing goes greater than the speed of light in vacuum, which is a fundamental constant of nature. So I just want to clarify that for sure. If we go speed of light per se, let's say we go to Pluto at speed of light, by the time we come back to Earth, it would have been decades. Well, first of all, we cannot go at the speed of light. It would have to be some speed. I think you're saying close to the speed of light. Yes, we could go to Pluto at 0.9 C and it will take however long, it takes to go to Pluto. Pluto is not exactly very close. And space-time will work differently, but I think Pluto will just take a very long time to traverse. It really depends on your speed. I don't know how close to the speed of light we can really go. So if you even light, so let's talk about light, right? So Pluto is both close and far. Everything is relative, right? Pluto is, so let's think about it. Jupiter is at 5.2 astronomical units from our sun. We are at 1 astronomical units from our sun. So Jupiter is already 5 times more distant. And then there's Saturn, Neptune, Uranus. Those are the planets, and then there's dwarf planets. Pluto is even farther away. So in terms of our own solar system, Pluto is quite far. But in terms of our galaxy, Pluto is not that far. So let me put something else in perspective. Our galaxy in light years is 100,000 light years across. What does that mean? It will take light, which goes at the speed of light in vacuum, 100,000 years to go from one end of our galaxy, to the other. So our galaxy is 100,000 light years across, which gives you some sense of our galaxy's size. And that, of course, the speed of light in vacuum, even though it's a fundamental constant, it is finite. It takes time even when you're going at the speed of light. And nobody can go at the speed of light other than light. So just wanted to clarify that. Wormholes are a thing in string theory. AE did say wormholes are possible. Albert Einstein, so yes, we talked about the Einstein-Rosen bridge. I've never seen that. I've never seen Albert Einstein, AE, like that. Interesting. Einstein. People usually just say Einstein. Einstein did work on the Einstein-Rosen bridge, which is a concept which basically gives us the first sort of official, I think it was the first official publication or notes on, which is the concept of wormholes. And we can talk more about that actually in a little bit. But we have also talked about that in the lives that we were doing in November. You might go back to my channel live tab and go look at the lives we did in November. We covered a lot of the physics from the 20th century there. And of course, we spent a lot of time talking about Einstein and his contributions. If speed of light is fastest, we can't even discover the next galaxy beside us in our lifetime. Speed of light is the fastest, yes. We can try to image, we actually have images of other galaxies. We can try to find things like that, but yes, going to another whole galaxy and things like that could be pretty hard. But then remember that, actually, I was gonna say, we can definitely look at the distances and try to get more idea about the distances better if you're interested in that. But yeah, it's pretty difficult. Okay, I'll let you guys keep on discussing and I'll continue the topic here. So I wanted to say that we do have certain other galaxy images that are also spiral galaxies, given that we can't really go outside our galaxy very easily because that's a very large distance to traverse and take a picture of our own galaxy. But we can have certain comparisons here. So here is that NGC, let me read the name again, NGC 891 galaxy I spoke about. We're looking at this edge on. See that dust lane in the middle? So this is an image of NGC 891 shown in the large binocular telescope first light image. Then we have the spiral galaxy M83 right there. This is an example, so that's M83 right there. This is an example of an image we have of a spiral galaxy that we took face on. And then of course we've shown Milky Way already. But here is the Milky Way galaxy. Artistic impression, again, why artistic impression? Because we can't really take a photo of the Milky Way very easily because we'd have to go outside of the Milky Way and do all that to take a photo face on or edge on, that is. Excuse me. So let me read this part to you, which might illuminate figuratively and literally some of the things about our own galaxy as compared with other galaxies, which could be fun facts, okay? So if you could view the Milky Way galaxy, or sorry, let me answer the question about the stars. I was about to do that and then I got sidetracked. So Joel says polarized radio waves. Hello. Hi, boss. Hi, Reese. Hi, Joel. Hi, everybody. Welcome to the live. So let me answer the question about how many stars, actually. That was the original question. Our galaxy's total luminosity of 23 billion solar luminosities. So luminosity is something, again, that we often put in terms of our sun's luminosity, L sun. Just like sometimes we put stars' masses in terms of the solar mass, like our sun's mass is one solar mass. So we will say masses of other stars in terms of the solar mass. We will say masses of other planets in terms of the Earth mass. Similarly, for the luminosity, we will often say luminosities in terms of the solar luminosity. Okay? So L sun. Ooh, and also we have a different sort of luminosity that we estimate for the disk of our galaxy versus the bulge versus the halo versus the grand total. So the grand total, let me just read it off actually. The disk we think is 19 times 10 to the 9 solar luminosities. Okay, yeah. Let us know when you're back and keep following the discussion. Actually, I kind of want some food too. The bulge is 2 times 10 to the 9 solar luminosity. The halo is also around estimated 2 times 10 to the 9 solar luminosity. So this is like 2 times or 2 billion solar luminosities. And the grand total is something like 23 billion solar luminosity. So now we will estimate some things. So our galaxy's total luminosity of 23 billion solar luminosities is fairly bright. Pretty bright. Like our galaxy is not one of the smaller, dimmer galaxies. It's a pretty, kind of like a pretty substantial big galaxy, actually. So it's fairly bright as galaxies go. If all the stars in the Milky Way galaxy were identical to the sun, which they're not, then we'd conclude that our galaxy contains 23 billion stars. So if we thought that every star was like the sun, and we estimated a 23 billion solar luminosity type of luminosity, then we would say, well, there are 23 billion stars. But actually, remember, we talked about the sun in some depth at one point, and we saw that the sun is actually pretty young, and it's on the main sequence part of its evolution. So there are going to be stars that are older or, more sort of like still forming, etc., etc. So most stars are actually dim little M dwarfs. So there's a type of star, M dwarf, that contribute little to the total luminosity, particularly in the B band. So the best current estimate, so taking into account the fact that our sun is a young sun, pretty bright, pretty spectacular in that sense, the best current estimate is that our galaxy actually contains 200 billion stars. So given that our total luminosity is 23 billion solar luminosities, we think that our galaxy, just the Milky Way galaxy, has 200 billion stars. So yeah, I don't know if Star Wars has been telling you that you can like go to other galaxies and go to other planets and their stars. I mean, exoplanets is something that we search for, but even that is very difficult, even within our own galaxy. But regardless of what Star Wars encourages, there's a lot indeed to explore, and it can be a little mind-boggling, the numbers, when you fact check the reality of the situation. So our estimate of the amount of stars is based on the galaxy's luminosity. Yes, galaxy's luminosity as a whole, and a little bit about the different parts of the galaxy too, and where we think what happens. So we'll get into that in a little bit here. So we don't think that star formation is equally active everywhere in the galaxy. So there are certain things like that too. So, oh, we got 10 likes. Thank you so much. Thank you for 10 likes. Can we get 20 likes? So if you could view the Milky Way galaxy from outside, which we can't easily, I mean, maybe we can in Star Wars, oriented so that the disk were edge-on, it would probably look like the galaxy NGC 891 that we just looked at, that edge-on one. And we saw that there was a prominent dust lane running down the middle of the galaxy. It is generally true for disk-dominated galaxies like the Milky Way and NGC 891 that the gas and dust is confined to a much thinner disk than the stars. So there is some things that we think about the gas and the dust and where that is, and we think that those are in a thinner disk, and then there's thick disks, and those are where maybe more of the stars are. I know, I'm so hungry too. Yeah. And he just said that he or she just said that they're getting food and then left us with so many questions. If you could view the Milky Way galaxy oriented so that the disk were face on, so this is the face on example of the M83 we saw, it would probably look like the galaxy M83. In this orientation, you can clearly see the most striking feature of galaxies similar to the Milky Way galaxy, their spiral arms. So that picture we saw, I'll show it to you again. The spiral arms, M83 is really the one that's telling us sort of what that looks like in real life. With real life picture face on, yeah, Exactly. So it's kind of like, it's like, say it's like there in the sky and we see it like face on, like its spirals are like this, whereas we could be edge on, as in its spirals are here, and we're seeing it like that. So Reese is basically edible. Oh God, that doesn't sound right. Sorry. Um, according to Joel, I didn't say that. I didn't do anything. If you could view the Milky Way galaxy, it would look like the M83 pretty much. In this orientation, you can clearly see the most striking feature of galaxies. Similar to the Milky Way galaxy, their spiral arms, disk-dominated galaxies like M83 and the Milky Way galaxy are thus referred to as spiral galaxies. And we pretty much have confirmation that that's what it kind of looks like and whatnot. Images taken at radio wavelengths indicate that the atomic and molecular gas tend to be concentrated along spiral arms. So we also have images taken at radio wavelengths, because remember I said that astronomy is done with various types of light, various wavelengths of light. And depending on which wavelength you're looking in, basically, you can see that there's more atomic and molecular gas concentrated along the spiral arms, with lower density ionized gas filling in the regions between the arms. So the spiral arms have some stuff, the regions between the spiral arms have some other stuff, etc. Images taken at ultraviolet and blue wavelengths indicate that the luminous, hot, and short-lived O and B stars, oh wow, O and B, stars also tend to lie along, sorry, I just remembered something else, tend to lie along spiral arms. So the luminous, hot, and short-lived O and B stars, those types of stars, different stars than our sun, tend to also lie along the spiral arms. So more of the, basically like more of the activity, hot and happening, quite literally, is along the spiral arms. Thus, the spiral arms are star-forming factories there where dense molecular clouds are converted into stars. And remember how we were also a dense molecular, or I don't know, some kind of gas cloud, probably dense molecular. And we were just some gas cloud nebula thingy thing, which condensated and made the sun and the planets. So the stuff that's in the gas or dense molecular clouds in some of these spiral arms could make future suns or future stars and their planets and things like that, just like we came to be. It's like they are our, future, not our future, I guess their future could happen in the future. So when those stars become stars and they get their own planets and things like that, you should consider moving there, my haters. The sun is located in a short stub of a spiral arm, usually called the Orion spur. So this is another thing. The Orion spur is a little bit of it's a spiral, it's part of a spiral arm. And this part of a spiral arm is nestled inside the bigger Perseus arm that is spelled as Perseus. So we're part, if anybody asks, where are you? We're part of the Orion spur, which is inside the Perseus arm. So we are in an arm, thank goodness. Otherwise, I would feel like we're boring. And then guess what? The Orion Nebula, the local hotbed of star formation. So we have a local hotbed. So I was mentioning all these like hotbed, gas formation, star formation, active types of parts of the galaxy, and Orion is one of them. But Orion is more in our vicinity of the galaxy. So that's the fun fact. We're close to that Orion Nebula. I mean, and again, by close, not that close. So Orion Nebula is in the Orion Spur. Orion Spur looks kind of close to us in this image, but again, close is really not that close. So those are certain things about our galaxy, and I wanted to now mention about the sun's rotation around the galactic center. So we have actually talked about this when we mentioned about evidence of dark matter in our own galaxy. I will remind you that dark matter is a very interesting topic. It is, in my list, at least the number 2 most unknown open question in the universe. The number 1 is dark energy. What is dark energy? We don't really know yet. What is dark matter? Number 2 question. We don't really know yet. But dark matter is interesting also in the sense that you can approach it in multiple ways. You can have an astrophysical approach, you can have an astronomy approach, those are pretty overlapping. And you can have a cosmology approach. We actually looked at it a little bit. We actually looked at it in a fair amount of bit in the cosmology approach as well. We have kind of covered it in all these different ways. And when we looked at it in the astronomy type of way, we basically mentioned evidence of it in terms of our own galaxy. The fact that we basically seem to have extra invisible matter in our own galaxy is basically your dark matter evidence at the astronomy level. Because we can't really, astronomy is more localized, it's more specific. It's more of our galaxy, certain astrophysical event in the sky, more specific like that. Whereas cosmology has to do with the entire universe and its birth and evolution and expansion. So the fact that we have dark matter evidence in these different ways is also very powerful. But we will kind of see why we need as in we discovered that apparently we have dark matter in our own galaxy as well. So and turns out that it is actually sort of a thing in a lot of galaxies, and it could play a very important role in galaxy formation. Right. So you will see that in just a little bit. So this particular astronomy. So Reese, were you here for the cosmology lives? Like we went over the critical density and the contribution to the critical density in cosmology in the universe, remember? So I'm just asking because there is different evidences. I don't know, I've slept since then. What? What do you mean? So there are various ways of looking at dark matter. Turns out that there is a contribution. Oh, okay. Turns out that there's a contribution to the critical density. Oh, well, I have a great memory, and I think you were here for the cosmology lives. So you would have been here for the critical density stuff. So the universe is made of 5 types of ingredients, and the ones that we understand are photons, baryons, and neutrinos. So wouldn't it be lovely if these ingredients could explain the critical density of the universe? But unfortunately or fortunately, they do not. And when it comes to the total matter density, it turns out that ordinary matter or baryon density contributes only like 5% to the critical density. So the rest of it, which we have different ways of measuring the total matter density, because remember there were ways in which you could get the matter density in a way where matter interacts with light. So it's like trying to understand how much matter there is in the universe in terms of its interaction with photons. And then there's also ways in which we can understand the total matter density in terms of gravitation and effects on gravitation. So from all these different ways, we saw that the total matter density was something like 30%, and ordinary matter or baryon density was only like 5% of that. So then the rest of it is dark matter, or 25% dark matter. So dark matter is the second most, majority ingredient of the universe. Yeah. So then, and the rest of it, 70% is now dark energy. And we also talked about how the universe has evolved, and it used to be more radiation dominated in the beginning, and then it became more right, like our measurement of the matter and how much of it we see through the light and gravitation is off. And the dark matter part, the one that does not interact with photons, is 25% of the critical density, which is all of the things in the universe's density in the current time. So again, I kind of sidetracked myself into that conversation about the critical density and dark matter evidence from that, because I wanted to make the point that we have evidence cosmologically of dark matter as well. It is one of those topics that you cannot ignore. There is this powerful, it doesn't go away-ness to dark matter, no matter whether you approach it from cosmology point of view or astronomy point of view or astrophysics point of view. And today, in just a few minutes, we will look at the galactic point of view, and our own galaxy too needs it / has it, and we were shocked, but here it is in your face type of thing. So an image of a spiral galaxy looks kind of like a hurricane. We will now talk a little bit about our galaxy and how the sun goes around the galactic center. So we, Earth people and Earth and the other planets in the solar system, go around the sun. In fact, our birthdays are determined by that, as in however many times we go around the sun becomes our age, something like that, once a year type of thing. Well, guess what? The sun goes around, and all of us along with it, because we go with the sun, right? Where the sun goes, we go, because we go around the sun. So we go around the sun, and the sun goes around the galactic center. And we will see. Bye. So there is also vacuum. There's also just vacuum and energy in the vacuum, which is dark energy. So don't get it confused. Dark matter is matter. And then there's also, yeah, make toast and hang around. And then there's also dark energy. So remember all of the things I said so far. I didn't really say anything about dark energy too much. So there's dark matter, then there's also dark energy. Okay. So, anyways, we will not be talking about dark energy today because enough is enough. I don't want to. I just want. I mean, dark energy is another favorite of mine. Yeah. It's not visible. It does not interact with light, but it does interact with gravitation. There is more matter there that we just don't know what it is. Yeah, what it's made of. That is. It has to be there, but we don't know how and where and what. What is the particle? So a specific question in this regard would be, what is the particle nature? Ooh, my microwave says 222. 222. I like that number. I like numbers. Well, I actually like words more, but I also like numbers. Huh, interesting. So, that's a great question. It could be. Pretty much. You can take a guess at it. Yeah, go for it. Take a guess. Could it not just be black holes? Maybe? We don't know. Concentrated pockets of mass? Maybe? We don't know. In fact, we remember we talked about it. There were some dark matter candidates we talked about, and macho was one of them. Remember the three main dark matter candidates? So, Reese, you could literally come up with a dark matter candidate, and it should probably be. Hey Siri, can you stop? Sorry, my. Hey Siri, just go away. Oh my god. Like I'm talking, and then suddenly, like my iPad is starting to. Whatever. So, pretty much any dark matter, say if you come up with a. Say if you come up with a dark matter candidate, pretty much, why not, right? It should be considered, we can consider it. But I'll just mention some of the dark matter candidates we already considered, which are, first of all, we thought neutrinos could be dark matter. Maybe neutrinos can explain it. Neutrinos are also very elusive. They also don't interact with photons. Remember, they interact through the weak force. But they were too low mass. So, sad story about this dark matter story where neutrinos are the main hero or heroine, because we think that, unfortunatamente, neutrinos are too low mass to really consider, to really account for all of the dark matter that we clearly have at hand here. Next candidate for dark matter was WIMPs. So we got inspired by the neutrino guess. Neutrinos do interact with gravity. Neutrinos do have a mass. It's a low mass, but they do have mass. So, our next guess, because we like to dream and we like to come up with guesses and we like to solve a problem as a community of physicists, was WIMPs, weakly interacting massive particles. This is because we saw that neutrinos don't really do a very good job of accounting for all of the dark matter. So what if there was an unknown particle out there called WIMP? Yes, now you remember. Yes. What if there was an unknown type of particle called WIMPs, weakly interacting massive particle, which is a lot like the neutrino, but we'll just make it hypothetically more massive and then look for it. So that's the next candidate. Then lastly, we talked about machos. massive compact halo objects, I believe was the full form of that, where because some people were looking for wimps, other people wanted to look for, you guys called it simps, but actually it's machos. So because of the wimp people, some people said, well, other people said, that is, we will look for machos, which will stand for massive compact halo object. These objects are basically sort of what you were asking about or guessing at. Basically very compact objects that are dim. So in a sense, they don't contribute much to luminosity, so we can't really like see them. But they are explainable types of things. They're like something like brown dwarfs maybe, or some stuff like that. In fact, I have the page right here talking about it. So brown dwarfs, old, cold, white dwarfs, neutron stars, black holes can all be machos if they're located in the halo of our galaxy. Machos, like any massive compact object, can act as gravitational lenses. So one of the predictions of the theory of general relativity is that massive objects can bend the path of light. So an early experimental support for general relativity actually came in the year 1919, when observations of stellar positions during a solar eclipse revealed that the sun had bent the path of the starlight by an angle consistent with the predictions of Einstein. We talked about this earlier. So because massive compact objects bend light, they can act as lenses. And so all of this kind of told us a way to see if enough machos could be found that can contribute to dark matter and account for dark matter. But basically, as far as our own galaxy goes, at least, only 20% of the dark matter in the halo can consist of machos. So there's still plenty of room for wimps in our galaxy or other explanation for dark matter in our galaxy. So all of that is to say, we still don't know what dark matter is. Okay? Do we know if this hidden mass is consistent throughout the universe, or could they? It seems to be throughout the universe, but it's not like the exact same distribution everywhere. No. So we will talk about that as well. So it looks like, so actually, let's do that right now. Let's finish the thing I was talking about so that we can arrive at that. So it's not the case that there is the same amount of dark matter just everywhere. No, that's not the case. But we have, another thing I should mention, the distribution of galaxies in our universe, period, is not random. So this is something also that we mentioned during our cosmology sessions. And, what's the point? Like, why not, right? Why does the distribution of galaxies in our universe have to mean something? The universe expanded, lots of things happened. It can be pretty much homogeneous, but that's not the case. So we think that dark matter actually has a role to play with that as well. And dark matter has a role to play within the galaxies also, in an individual galaxy. So we will get some idea of that in this discussion. So it's a very, it's an involved topic. It's not the number 2 or even number 1 most open question in the universe, because it's very easy peasy, right? A lot of smart people work on it, and they're still not really able to conclude what it is. So it's not really something. So what I mean by not random is that the distribution, like, there is some meaning, or it's not, yeah, There's some meaning, some shape to it. So I don't want to get derailed by the entire universe right now because I want to talk about our own galaxy. So let me continue. So if we were to see the galaxy from the viewpoint of that face-on view that we saw for M83, but we can't for the Milky Way because we live in it, we would see the stars of the disk moving in a clockwise direction. That is, the disk is rotating such that the spiral arms are trailing. Stars in the disk are on nearly circular orbits, close to the midplane of the disk, all orbiting in the same direction around the center of the galaxy. Yay! We all orbit in the same direction around the center of the galaxy. By contrast, stars in the halo are on elongated orbits at random orientations relative to the disk, with some moving in the same sense as the disk stars and others moving in the opposite sense. So what happens in the spiral arms is sort of different from what happens in the halo. This is why, remember, we mentioned that the galaxy has three major components: disk, bulge, and halo. And I'll say it again, what a halo is. It's the third component of our galaxy, and it's a roughly spherical distribution of stars about 100 kiloparsecs in radius. Thus, it extends far beyond the disk. So the halo is more like halo, around, even one might say, the galaxy. So a roughly spherical distribution of stars about 100 kiloparsecs in radius. Thus, it extends far beyond the disk. The halo has the same luminosity as the bulge, which we talked about, but its stars are spread over a volume around 10 to the 6 times larger. The three stellar components of our galaxy, disk, bulge, and halo, differ in their stellar populations as well as in their size, shape, and kinematic properties. So we talked a little bit about how there are sort of like older or newer stars depending on where in the galaxy you're looking. Does a galaxy itself have a gravitational? Yes, of course. What do you mean? Every massive object has a gravitational field. So the galactic center has a supermassive black hole, and the galactic center is very, massive. So we are orbiting that around a yes, we're eating. Yes. We are eating a neighboring galaxy. Yes, I would say we have a gravitational field. Indeed. Yes. So, yeah, we're a bunch of mass who is attracting other mass. Yes. So actually, let me mention really quickly about the stars too. The thin disk contains relatively, so we mentioned how the disk, the bulge, and the halo will have different populations of stars, different kinematics. Yeah. Yes, we're eating that galaxy, I believe. Yeah. I think it's Andromeda that we're going to be eating. We will just merge together. That's all. Just a friendly merge. No harm, no foul. We're bigger. Bigger things eat smaller things. As simple as that. We will actually talk about the merge and how things will be mostly very unharmed. Actually, totally unharmed. So these parts differ in their stellar populations. The thin disk contains relatively young stars for the most part and is where most star formation is occurring today. So the thin disk contains relatively young stars like our sun, Thin disk stars tend to be rich in metals, so has more metals, so more elements heavier than hydrogen and helium. In the jargon of astronomers, stars that are young and metal rich are called population 1 stars. By contrast, the halo contains stars that are relatively old and low in metals. And these older stars or metal poor stars are called population 2 stars. And then, of course, the thick disk also has stars, and these are more intermediate in their properties between population 1 and population 2. But all things considered, oh, and the bulge contains a mixture of old and young stars as well. But all things considered, the halo, which is going to be important to understand, sort of at least what the halo is, the halo has the older metal poor stars. So older meaning older, closer to the beginning of the universe. Like the first set of stars we made in the universe are going to be metal poor. Because remember, the Big Bang gave us hydrogen and a little bit of helium, and everything else has to be made in the stars. But as stars, get formed, go through their life cycle, die, make more stars, well, the later stars are going to be more metal rich because they are coming from the remains of the older stars. So very different very different story between these types of stars. Okay, population 1 stars or metal rich stars versus metal poor stars are very different things, and the halo has more of the older stars. And you will see that, well, I don't know if you will see, because there are missing pieces in all of this, right? We don't know what dark matter is, and you will see how dark matter is important in the halo later on in this discussion. So as far as exactly what role, we know it probably plays some role in the halo, in the galaxy formation, in the universe itself, and all that. All things considered, dark matter plays some role, some important role in all of this. And it would be nice to understand that by further studying it and understanding it. So anyway, so those are the different parts of the galaxy. So we can understand about a star, for example, by taking data on it and looking at its spectral lines. Observation is the short answer. So that is the disk is rotating such that the spiral arms. So I went back and defined out the disk and the halo and all that, so that this part will be clear. But now let's keep going. Stars in the disk are on nearly circular orbits, close to the midplane of the disk, all orbiting in the same direction around the center of the galaxy. By contrast, stars in the halo are on elongated orbits at random orientations relative to the disk, with some moving in the same sense as the disk stars and others moving in the opposite sense. On much different length scales, the disk of our galaxy can be compared to the planets in the solar system, while the halo of our galaxy can be compared to the Oort cloud. But whatever. The sun's orbital speed. So we know that we're going around the sun, and the sun is going around the galactic center. But you might ask, at what speed? So the sun's orbital speed around the galactic center is around 220 kilometers per second. That is around 225 kiloparsecs per giga-year, or per billion years. So not bad of a speed per billion years. And in these types of scales, really the time scale is more of a billion. Billion is normal. It's not like you don't expect or compare it to our types of times, like years and all that stuff, decades. Thank you for liking the live. So later on, we'll discuss how the orbital speeds of the sun and the other stars are actually determined. But for now, let's just consider the implications of this orbital motion. So we also know that the distance of the sun from the galactic center is 8 kiloparsecs. So that's how far we are from the galactic center. Oh my gosh, now I want some pasta. Thank you for liking the live. Can we get to 20 likes? So we know we're going at that 225 kiloparsecs per giga-year speed, and our orbital radius is around 8 kiloparsecs. So now if we make the approximation that the sun is on a perfectly circular orbit, we find that its orbital period is around 0.22 giga-years. So the sun is around 4.6 giga-years old only. So it has gone around the galactic center just over 20 times. So the sun's age, sort of in the galaxy, if you will, in terms of how often or how many times it has gone around the galactic center, is around 20. So it is not quite a teenager anymore, still a very young star. So that's another perspective on the sun. So now we have, of course, Kepler's third law giving us all the, all that stuff about the mass and the orbital period and things like that. You've never had pasta? Thank you for liking the live. Can we get 20 likes? So to find out how much mass is inside the sun's orbit, we may use Kepler's third law. So this stuff will be very important, as you will see in a little bit, because we will have a shocking result soon. So pay attention. So m sun plus mg is going to be a cubed over p squared, where we know that comes from Kepler's third law. Hello, Eddie Buongiorno, teacher. Good morning in Italian, I think. Thank you. Good morning. So mg is the mass measured in solar masses inside a sphere of radius . So m sun plus mg is equal to a cubed over p squared. This will be in the quiz later on, so listen up. mg is the mass measured in solar masses inside a sphere of radius 8 kiloparsecs, centered on the galactic center. A is, of course, that semi-major axis, 8 kiloparsecs in this case. P is 2.2 giga-years. Or sorry, 2.2 times 10 to the 8 years. It's 0.22 giga-years, so 2.2 times 10 to the 8 years. Strictly speaking, it must be confessed, we can only use Kepler's third law if the two bodies involved are spherical, but we're going to go with it. Since the matter distribution of our galaxy is flattened, the mass mg computed from this will be slightly inaccurate, but it will still be good enough for the first estimate. Thank you for liking the live. Can we get 30 likes? So good enough for the first estimate. Since the mass of the galaxy is much greater than the mass of just one star, we may assume that mg is much, much, much bigger than m sun, of course. Mg is all of the mass inside the sphere of 8 kiloparsecs. So mg is literally m galaxy inside that 8 kiloparsec radius, which is where we are located, right? Because of the sun being located there. So now it's really mg is about equal to a cubed over p squared. Putting it all together, we get that mg is around. So this is just from the orbital speed and all of this calculation and Kepler's law calculation. We're getting that mg is around equal to 9.3 times 10 to the 10 solar masses. So 93 billion solar masses is a lot of matter, especially when you consider that the total luminosity of our galaxy is merely 23 billion solar luminosities. So from the gravitation standpoint, we're getting 93 billion solar masses within 8 kiloparsecs, remember, because that was the radius at which we're doing this. So that's a lot. We were like, okay, we're getting 93 billion solar masses of matter, especially when we know that the total luminosity luminosity of the full entire galaxy. Oh my God, I hit my hand. The entire galaxy's total luminosity was 23 billion solar luminosities. So luminosity given in the solar luminosity unit. The material of which Tare Zamin Par. Hello! Thank you for naming a movie. The material of which our galaxy is made must have, on average, a higher mass to light ratio than the sun. However, the mass of mg that we've just now found, the 93 billion solar masses, contains only the mass inside the sun's orbit. So we're like, okay, we did this calculation, and also this is only inside the sun's orbit. The mass outside the sun's orbit has no net effect on the sun's orbital motion. So for stars and gas in the disk of our galaxy to be on stable circular orbits, we require V of r squared over r is equal to gm of r over r squared, where V of r is the orbital speed of a star on an orbit of radius r, and m of r is the mass inside a sphere of radius r centered on the galactic center. So we can thus determine the mass inside a star's orbit from its orbital speed. This is just getting its mass from its orbital speed relationship. So we are getting m of r is equal to v of r squared times r over g. Most of the galaxy's luminosity is provided by the disk. We know that too, because we know that from the previous discussion about the disk versus the other parts. The disk's brightness falls off exponentially with a scale length of around 3 kiloparsecs. So luminosity is a big component of this discussion. It's about finding mass and then not finding the luminosity that should go with it, basically. It's like, okay, if we have a bunch of stars that we just didn't know, like, where is the mass, right? Most of the galaxy's luminosity falls off after about 3 kiloparsecs. Thus, most of the galaxy's luminosity lies inside the sun's orbit. So we've got this information about the mass that we think lies inside the sun's orbit based on orbital speed. But then we also know some information about luminosity, which basically kind of falls off. And because of the scale length of that falling off at around 3 kiloparsecs, we know that, okay, the luminosity providing things are all within the sun's orbit, the sun's orbital radius, because the sun's orbital radius is, or sun's orbit is 8 kiloparsecs, and all of the luminosity is within around 3 kiloparsecs. So if most of the mass lies inside the sun's orbit as well, we would expect that m is sort of a constant for r greater than r naught, where r naught is where we are. And, let me also mention a side note. Because m is equal to v r squared, v of r, or really v squared r over g, now you put that in, m should be about a constant. Hi, Mehrana. For r greater than r naught is where you're doing this calculation. Then v should be going as roughly r to the minus 1/2 after you do the math. So observations of stars and gas clouds in our galaxy reveal. So this is what we think should be happening. all of the luminosity producing things are well within the sun's orbit. So we think that, okay, outside of that, m should be sort of a constant, so the orbital speed should be going as r to the minus 1/2. So the orbital speed should be it should be slowing down, in other words. Right? Because gravitation is proportional to 1 over r squared. So if you're farther away, you should be slowing, your orbital speed should be slower. And it's like, oh, so much luminosity is within that 3 kiloparsecs, actually. Thank you for subscribing. Thank you for liking and sharing and subscribing and being here and commenting. Love it. And thank you so much. So it's like, okay, all of the luminosity producing things seem to be well within the 8 kiloparsecs. It's actually kind of falls off after 3 kiloparsecs from the galactic center. So why so we're getting there. Keep on listening. We're in the middle of the calculation which leads to something. So we have to keep on going for a bit here. So the logic is, right now we don't know about dark matter yet in the galaxy. We're getting there. So we're seeing that the sun goes at a certain orbital speed. From that orbital speed, and knowing where the sun is, how far from the center of the galaxy, which is 8 kiloparsecs, we get an estimate for the mass that is within that 8 kiloparsec orbital radius. And that mass is the mass of the galaxy, all of the things in the galaxy, especially within 8 kiloparsecs. And then we also know separate information. Most of the galaxy's luminosity is provided by the disk, whose brightness falls off exponentially with a scale length of around 3 kiloparsecs. Thus, most of the galaxy's luminosity is within the sun's orbit. So this is another piece of information, which is that we know that the luminosity producing stuff, things that are bright, are within around 3 kiloparsecs, or it falls off a lot after 3 kiloparsecs. So it's well within the 8 kiloparsecs. So now we're thinking that, oh, okay, we have a mass for all of the stuff within 8 kiloparsecs. We have a luminosity for all of the stuff within the 8 kiloparsecs. Okay, so maybe most of the mass is within that 8 kiloparsecs, the luminosity, etc., etc. And so now, once you move out from that 8 kiloparsecs, your orbital speeds should be slowing down of the things that are farther away from the galactic center and still rotating around the galactic center. But is that the truth of the matter? The Keplerian orbits, Kepler, right? He gave us a law, 3 laws. The third law has to do with the orbital period and everything. We think that orbital speed as a function of distance from the galactic center should be kind of like falling, because we think that pretty much most of the mass of the galaxy should be well within the 8 kiloparsec. which is also where the luminosity is. And we have an idea for how much mass because of the sun's orbital speed. But what do we observe? We observe that based on observations of stars and gas clouds in our galaxy, that reveals that the orbital speed v in the disk does not fall off with distance from the center. Instead, all the way to the outer fringes of the disk, the orbital speed is constant or even slowly rising with radius. Yeah, that's one of the biggest evidences, yes. Thus, there's more mass outside the sun's radius than inside. Which is a shock. So, let's say that you find that there is a frick ton of mass within the 8 kiloparsec radius number. And then let's say you also see all of the luminosity is pretty much within that radius as well. You would think that that's where all of the mass is. That's it. That's where the galaxy has its mass. That's where the galaxy has its matter. And the orbital speeds of things farther out should be slowing down. But that does not happen, which is contrary to what we would have thought. So instead, all the way to the outer fringes of the disk, the orbital speed is constant or even slowly rising. Thus, there is more mass outside the sun's radius than inside, which is a shock. We would not have thought that. If we estimate, say, if we estimated, oh, here's the picture. This is the orbital speed versus the distance from the galactic center. See how this would have been the Keplerian orbits, but instead we see this behavior of the speeds slowly rising. So let's say we take an orbital speed of around 270 kilometers per second, which is more than our own orbital speed. The sun's orbital speed is 220 kilometers per second. Let's say we pick a bigger one from that plot, and we say that this is happening at r equal to 2 r naught, which is 16 kiloparsecs, because we are at 8 kiloparsecs from the center. We would find that the mass inside that radius is 2.7 times 10 to the 11 solar masses. So a ton of mass. Since v, the orbital speed of stuff, is roughly constant outside the sun's orbital radius, and mass must increase as m is proportional to r, implying an average mass density of rho going as r to the minus 2 in a region where the luminosity density is plummeting exponentially. So the confusing thing is that orbital speeds stay constant or even slowly rise as you go out. And on top of that, the luminosity is plummeting exponentially. This stuff can't be seen. Luminosity contribution is nothing from these things, but the mass seems constantly going up. So this is why, literally, it is dark matter. That's why, okay? The leading explanation is that there must be dark matter in the outer regions of our galaxy. So yes, I think you asked about the halo. Yeah, your mass keeps on growing as you go out. Wait. And your luminosity plummets exponentially. I got 30 likes? Oh, I got 30 likes? How did that happen? Thank you, everybody. I got 30 likes. 31. Oh. Okay. Since V is roughly constant outside the sun's orbital radius, the mass must increase as m proportional to r, implying an average mass density of r to the minus 2, in a region where the luminosity density is plummeting exponentially. So things are getting darker and darker, but somehow the mass is going up. And the density of the mass is going up, not just the mass. Mass density is going up and up and up, where luminosity is going down and down and down, and that too in an exponential manner. Getting darker. Dark, if you don't like dark, well, this galaxy on the outer regions may not be for you. It gets very dark compared to where more of the light is, which is all within mostly 3 kiloparsecs of the center. And we are at 8 kiloparsecs from the center. So you would think that all of the stuff is mainly happening within that 8 kiloparsecs. We were thinking that we're really hot and happening, but turns out there is things we don't understand, such as this dark matter. There is matter, but it's dark, no luminosity. Whoops. And the leading explanation is that there must be dark matter in the outer regions of our galaxy. The phrase dark matter is the term used by astronomers to refer to matter that is too dim to be detected using current technology. So maybe it's too dim, maybe we just suck, I don't know. The obvious question to pose is, what is the dark matter? It's hard to determine what something is made of when you can't see it. In recent years, there have been 3 major candidates to play the role of dark matter. We talked about this already briefly. Those are neutrinos, WIMPs, and machos. We just mentioned them. But that's the story. Even within our own galaxy, because of this orbital speed versus galactic or versus distance from the galactic center. So orbital speed versus distance from the galactic center evidence. This is sort of an undeniable evidence of something extra. Invisible matter, dark matter, dim matter, doesn't produce luminosity matter evidence. And this is what we are talking about when we say dark matter. It's not that we have found something and we're calling it dark matter. We have found evidence of, like, oh my God, this doesn't make sense. There seems to be more matter there, but we don't know what it is, and it affects things in a gravitation sort of way. And here's this orbital speeds that don't make sense. No, it's not the absence of matter. It is the presence of matter, but the absence of luminosity. It's matter that does not contribute to luminosity. There is a big difference. So it's not producing flux of light. It's not luminous. It doesn't interact with photons. It's there, but we can't see it. Can't see it. Dim, elusive matter. So now, what else is dim and elusive? One might ask. Yeah, you're like dark matter? Yeah. What else is dim and elusive? Well, you might remember when we talked about neutrinos, neutrinos are a type of particle that is kind of elusive, also does not interact with photons. So we thought the first candidate was neutrinos because of this reason, but then turns out that probably neutrinos are too low mass to really account for all of this dark matter. And then WIMP's second candidate, we'll see what happens, what shakes out of that. The search is going on for WIMPs. And then we also mentioned Macho, the massive compact halo object. And from what we could understand with the gravitational lensing effect is that probably the Machos don't really all account for all of this dark matter either. So long story short, it's gonna be the WIMPs probably, but also we don't really understand or know what WIMPs are, particle nature of these things, because the research is ongoing for that. So that's where we're at with this dark matter story. It's an active area of research. It's an open question in astronomy, astrophysics, physics, and cosmology. We have a cosmology story of dark matter as well, which matches this type of evidence and finding and points towards the importance of dark matter and the role it plays, of course, in our critical density, in forming galaxies, etc., etc. So let's say if you accept that dark matter is a thing, we don't know what it is, but it is a thing, and it would explain this orbital speed stuff. Well, then you could take a step forward. You could take it many steps forward. So the dark matter experts basically have accepted there is dark matter, and they even might look into, oh, so this stuff is in our halo, and like why and what role does it play in making the galaxy? Does it have a role in making the galaxy? We think so, probably. There is some thoughts on that. And also, what about other types of galaxies? What about completely different galaxies? Because this is a spiral one. This is a beautiful spiral galaxy with a lot going on. But then there's other galaxies that are kind of dim, kind of not as pretty, kind of completely different. And we find that dark matter might play a role in those galaxies as well. So we can actually cover more types of galaxies next time. I wanted to talk about our galaxy and talk about how dark matter is a topic even in our own galaxy. It's undeniable and a question mark even in our own galaxy. So of course it's relevant. Of course it must be studied, But yeah, understanding our own galaxy is of course important. It is our galaxy. But dark matter has a role in completely different galaxies as well. Since the oldest stars are in the halo and black holes come from dying huge stars, the chance of there being black holes in the halo is more likely since the oldest stars are in the halo. Okay. So, if the star is still a star, then it's not a black hole. Black hole is a stellar remnant. I mean, I'm not so dark matter, let me preface by saying that dark matter is an open question. Anything anyone wants to guess at for dark matter candidate is totally valid. And black holes of some kind, black holes of some nature may indeed I don't know. We just don't know. The answer is, are black holes dark matter, or are dark matter just a bunch of black holes, maybe smaller ones or something? I don't know. The answer is, I do not know. But I do know that as far as black holes related with stars are concerned, an older star is just an older star. The star would have to die in order to make a black hole. Does that make sense? But yeah, I don't know. There could be. The answer is, I don't know. I would I think people have made and here's the thing. I think basically what you're suggesting is a subset of the macho theory. Since there's old stuff, are you saying because there's old stuff there, they would have had more time to die? Okay. Here old means metal poor stars that are from, like, it means generational. It's not that they have, basically, I love it. Black holes are batteries from which energy can be created. Oh, okay. I missed that comment. Thank you, everybody. So, old star. They're old in the meaning of population. But they're metal poor. I would say the better way to put it is metal poor. Old as in generationally old. Metal poor, they don't have a lot of metals, etc., etc. But your guess about black holes is not a bad one. So regardless of whether the stars are old or not, I think the better word there is metal poor versus metal rich, right? So it's fine. It's all good. So so now what we could talk about is the black holes. Let's say, black hole as oh yeah, there is a kitty cat. There's some kitty. Oh, there's Baji. Why isn't the cat involved in this conversation? Yes, there's Baji. Oh, thank you for asking. Baji could suss this out. Yes. The cat has its own theories as well. Yeah. Oh my gosh. I almost fell from my chair here. Oh my God. Are you kidding me? I tried to push it. Okay. So I am so excited for this topic. And you guys are being so nice today. Usually everybody's distracting with their weird comments. So I'm so excited. We're finally talking about something relevant to this channel and the content. So your guess for a black hole is not a bad one at all, Reese. In fact, you guys are hilarious according to you. You're so funny according to you. There's Baji baby. Oh, Baji Shana. Hi baby. Look at Baji. So basically, there's the black holes that we have talked about in relation to massive stars' death. That's a stellar remnant. Okay? So stars, when they die, regardless of metal richness or metal poorness, let's just now consider stars, and depending on their mass, really it depends on their mass, they will die. And how they die, when they die, there's some more details. There's a lot of details when it comes to stellar physics. But regardless, we know that stars, when they die and make a dead body star or dead body stellar remnant, that is either a white dwarf or a neutron star or a black hole, depending on their mass. So now let's forget about the stars dying and all of that stuff. Let's just say that the dark matter is black holes or brown holes or dim things. Like black hole is sort of a more specific term, right? Let's say it's just a dim object. Sorry, I meant brown dwarf, actually. There is a thing called brown dwarf, in fact. Okay? And again, what is a black hole, right? It's a compact object. In fact, it is so compact, there's a singularity. So it's an amazing topic in itself, and we have talked about black holes too, but right now let's not focus too much on the details of a black hole, but on the fact that we are basically considering compact object as the candidate here for dark matter. Compact object, kind of dim, kind of not really contributing to luminosity, because the biggest thing here is that the mass or the matter that exists beyond, that radius is dim. The luminosity plummets exponentially. But the matter is more. So what could it be? What could it be? And your guess was black hole, but really, let me reframe that as a compact object, right? A black hole is just an example of a compact object. So a compact object which is dim, doesn't really produce much luminosity, can't really see it very easily, that type of thing. That's basically what we already considered. Remember, the machos. They named it this silly name, macho, because the other candidate is called wimp. But macho basically means massive compact halo object. Halo object. It's something like what you're saying, maybe black hole, maybe brown dim thing, brown dwarf, other dim thing. In the halo, massive and compact. Now, massive is good because they would be massive, because we're trying to account for a lot of freaking mass. The more massive, the better for these things that are so dim, apparently. And compact kind of goes hand in hand with the fact that when a star is generally burning and still alive and very luminous, even dim stars have luminosity. When they die, though, they make compact objects of different kinds. We don't have to go into exactly what, but let's just say we accept that they become compact objects after their death. And those things have less luminosity, for sure. Still, they usually have some luminosity, but they have less. So let's just say that your candidate of choice is basically this compact object halo, in the halo type of thing. We already considered that. It's basically in that macho bracket. And remember, we were trying to figure out how many of these are there and if they can account for if they can account for dark matter or not by looking at gravitational lensing. So massive compact objects, even if they're super dim, can't see them, so hard because they're not luminous, etc., would still act as gravitational lenses. So by looking at gravitational lensing way, we figured out that, yeah, there might be some machos, there might be some compact objects in the halo that could account for dark matter, but this is saying that it's only 20% of the dark matter in the halo can possibly consist of machos. So unfortunately, from the gravitational lensing way, we don't find enough of these things. There's not enough compact objects in the halo to really contribute to all of the dark matter that there is, all of the matter that is still under question. So, also known as dark matter, because we have to give it a name, right? We found, oh my God, there's this matter that we can't explain, and then there's all this talk that goes with it. So we have to give it a name. And we don't know what it is, but it's called dark matter. The thing we don't know is dark matter. So, and we had these candidates for it. Neutrinos, WIMPs, machos. Machos is basically the compact object thing that you're guessing at. And that's a completely valid guess. But unfortunately, they would still be gravitational lenses. And with that, we don't see enough of that happening to give us all of the dark matter. So it is still a very much open and unknown thing, open question, which we must probe further. Could black holes be extracted for energy? I am not a power engineer, so I don't know. Which black hole? The supermassive black hole at the center of our galaxy? It is 8 kiloparsecs away. You can see if that sounds like a good source for you. I wish. The universe came from an event called the Big Bang, which was neither very big nor very bangy, but yeah, another singularity. I don't know about the white hole thing you're saying, but the universe came from the Big Bang. We also talked about the Big Bang on this channel various times. And we talked about Big Bang nucleosynthesis and what things were there in the very early, hot, dense, young, energetic, crazy universe. Mainly photons, positrons, and electrons, and a little bit of, well, some neutrinos. But mainly the cosmic plasma was photons, positrons, and electrons. And some neutrinos and some baryons. And the baryons were mainly hydrogen and helium and trace amounts of lithium, but mainly just mostly hydrogen. And then now the pop quiz is, what is the most abundant element in the universe? Somebody say it. Somebody, I'm sure you know it. So that is the story here. We also looked at, so this is the astronomy way. I keep saying that there are various standpoints, various viewpoints to look at this with. Dark matter is such a topic that is pervasive in various subfields. In astrophysics, it plays a role. In astronomy, it plays a role. In our galaxy, it plays a role. In neighboring galaxies, it plays a role. In the universe, it plays a role. It is a major ingredient. It's not the most major ingredient, but it's the second most major ingredient in the universe. Oh my God. And hello, Woodlife. And now I've lost my train of thought. There's a cosmology point of view, which we've also talked about. So the thing to note here is that we looked at this phenomena, this dark matter topic from the point of view of our galaxy, which is more of an astronomy thing. But there is also cosmology ways of looking at dark matter, which I encourage exploring as well. And we have explored on the channel as well. So keep in mind that dark matter is not just a universe, or it's not just our galaxy type of thing. It's not just a neighboring galaxy type of thing. It's also a universe type of thing. And so we can approach it in those different ways. Dark energy, on the other hand, also a very open question, is absolutely a cosmology type of thing. So if you say don't care about dark energy, then don't go into cosmology, because cosmology is gonna be interested in dark energy, because it's the biggest majority cosmic ingredient at this point, and is responsible for the expansion of the universe. And that topic is heavily studied in cosmology. Whereas dark matter, you can study it in an astronomy way, astrophysics way, cosmology way, particle physics way. Another thing I forgot to mention, because some people, care about finding more types of particles. We know that more particles are discovered all the time. They used to be discovered more often in the late 1900s and early part of this century. We discovered the Higgs boson in 2012. So as recent as that, I guess that is kind of a long time ago at this point. But we know that new particles being discovered is not so crazy anymore. It used to be that quantum mechanics was considered crazy and bizarre, but at this point, the success of it has led to a whole another field called particle physics, where we discover particles all the time. So dark matter, again, can be studied as a particle physics standpoint, finding the particle nature of dark matter. Maybe you smash some particles together in a collider or something, get some signature out of a WIMP or something. That would be the particle physics approach to finding dark matter. So I just wanted to encourage that there are several types of ways in which one can study dark matter, explore it, get into it, and understand more about the topic, and then you would be contributing to a much larger topic, right? Because it's all pervasive, it's important in the universe as well. There's lots of motivation to studying dark matter. Whereas with dark energy, which is cosmic ingredient number 5 that we discussed during our cosmology lives, which is 70% of the critical density. Also, an open question, what it is we don't exactly understand or know, is much more of a large scale phenomena only, okay? So dark energy is experienced at larger scales in the form of the expansion of the universe. So it's not our galaxy, neighboring galaxy type of thing. It's more of a larger scale type of thing. And so if you want to ignore it and you care just about smaller scale stuff in the universe, then that's fine. You could ignore it. Not everything has to be studied by everybody. But I wanted to inform people about the status of things and what things are going on and what are the biggest questions in the universe at this time. And hopefully it inspires many of you to go out and study these topics. The book I bought about planets, the black hole is the most important to survive even when it seems impossible. What do you mean? In terms of the dark matter candidate, or you mean that the black holes in the world, or sorry, in the universe, should be surviving? Black holes are pretty good at surviving, I think, in general. They're kind of like good, you know? They can get bigger depending on what they eat. Oh, sorry, I was not... Somebody said not to mention eating because people are getting hungry. I am hungry, actually. But I love this discussion. Yay! Ah! This is so much fun. Aren't you hungry? Sort of. So, okay. Okay. You know what? Next we will talk about... Oh, you know what? Ooh. You know what? I'm gonna time out wood life because I don't appreciate you. I wish that there was a longer time period I could time out this person. But I don't want to derail my lives anymore. Hello everybody. Thank you for being here. I actually, Steven! Steven, how are you? James Woodlife. If you cannot contribute some knowledge about planets or the galaxy or the solar system or the universe, then I will not let you back in. I've had enough of you. Quite enough at this time. So I think people were entertained by this, but I am not anymore. I never was. I was just being accepting. But you're taking advantage of me and my face. So you're timed out for 24 hours. I couldn't see the bigger option. I'm good. Yesterday was the 4th. Oh, I'm sorry. We missed you on the live, Steven. But I'm glad you were spending time with your mother. Okay, so now, let me show you some examples. Sorry. I'm just a little... sorry. I'm thinking about something else. It was a good day, no snowfall, but still got snow from 2 weeks ago. Yeah. Oh, when did we get our snow? When was it? When did Boston get snow? Was it Sunday? I can't remember any of the days anymore. My memory has been erased. Oh God. It's a little late. Gosh. Okay. We got a light snow during this past. Nothing to bring. Aw, did it not snow as much in Virginia? Ooh, it snowed a bunch in the south today, right? Or last night? Did you not get the North Carolina type of snow? I look so tired. Gosh. Okay, so why are you still up? It's almost 4. It's 3:30. I guess it's 3:30. I'm looking at the clock in all kinds of ways. Why are you still up, Steven? I am hungry. I'll be charging the phone soon, so maybe I'll eat then. But anyway, so I wanted to show you guys, I wanted to leave you with some I heard. No, just a light dusting here. Some nights I cannot sleep. Oh, okay. That's fine. I'm glad you're here, Stephen. Stephen, if you want to rewind, we talked about our galaxy, about the different components, main components of our galaxy, and compared it with some other galaxies that we can image. Of course, we can't image our own galaxy because we're in it. Not easily anyway. We'd have to get out of it first. As in, if we wanted an edge on or face on picture. So we talked about our galaxy, its various parts and components. And then we talked about one of the most shown, most well understood evidences of dark matter, which is, of course, the orbital speed versus distance from galactic center plot. And the orbital speed of stuff was going up or staying constant or even slowly rising outside of the I know about the spiral galaxy, but I don't know about Nard. I don't know about that. So I do know that it's a spiral galaxy. I don't know what that other word means. There are some words that I'm still learning. They consider the Milky Way as a... Okay. So, oh my God, my neck. Oh my God. Okay. So, indeed. Indeed. Oh, Bard. Do you mean that there are... Yeah, I don't know what you mean. Like thin disc, thick disc, that sort of stuff. Well, Stephen, you should rewind, is what I was trying to say. We spoke a lot about our galaxy, some really interesting facts about the galaxy, and we talked about dark matter evidence in our galaxy with the orbital speed method. So rewind and go watch it, Stephen. And can you like the live? Did you like it? Like the live, please. Thank you very much. Like the live, and can you rewind and go listen to the dark matter stuff we talked about and the galaxy stuff, and then leave me a comment, and I'm gonna maybe get something to eat. Actually, I'm kind of hungry. Oh, I know. I can make some bread and cheese type of thing. Okay, hold on, guys. Hang in there. Hold on. Near the core, they say there are about... Well, we talked about the discs and the spiral arms. You should go listen. We talked about the spiral arms. We talked about the various arms and things like that, and what type of stuff happens in which areas. Like the arms have more of the star formation and all that. Okay, so all right, give me a moment. I need to charge the phone. Oh, and what I'll do is I'll let you look at some pictures while I do that. You know what? I think what I'll do is show you some other examples of galaxies, because we have already looked at the Milky Way and similar galaxies. So because next we might talk about other types of galaxies, let me leave the phone charging and me making some toast with this type of thing, some other types of galaxies. So We can talk about galaxy classification. Oh, there you go. There's the word that Stephen was talking about. Here it is. Oh, so it's a further classification of spiral galaxies. Here you go. You can look at that. Many spiral galaxies, perhaps even the majority of them, have an elongated central bar of stars. Barred spirals, like ordinary spirals, can be further subdivided into S-bar, SBB, and SBC. Got it, got it, got it. We're in the Perseus arm, but in the Orion spur. I love Boston, spent 2 weeks up there. Oh, interesting. Family history, huh? I like Boston. I like it a lot. Barred spiral galaxies. Wow, Steven, you manifested this. Okay, I'm gonna let the phone charge and maybe eat a little bit, and you guys can enjoy these pictures. And thank you everybody for being here, and you can rewind the live as well to see more of the content that we covered, especially on our own galaxy, as well as the dark matter evidence and some dark matter candidates and certain other features of our galaxy and things like that. So, and how often the sun goes around our own galactic center as well. So all those types of things are in the live. Go back and listen to it. You just have to rewind towards the beginning and have fun, and we will continue here as well. Thank ya. Look at that. Interesting. These are some interesting shapes. Ooh, and also when we look up at the night sky, most of the things we're looking at are galaxies. If you thought that there were a lot of stars in our galaxy, well, there are also just a lot of galaxies, period. So here we are looking at some galaxies right here. Oh, really? Ben, I didn't realize you were here. Thank you, Ben. In Plymouth. Oh, wow, pretty. That is pretty. Good night, Ben. I didn't realize you were here, Ben. Did you like the Galaxy stuff? Hello. Oh, look at you guys having a nice chat. Very nice. Here's another galaxy. Look how different this is. This is a dwarf spheroidal Leo 1. Hello. Hi. So leave that light on. Look at how weird that is. So very, you know, shapeless almost. A dwarf galaxy. Welcome back. Yes, thank you. Great uncle stories. Hi, Sachi Mama. Which movie are you talking about now? Yes, Sachi Mama. Come. Fuji. Come, Fuji. The right stuff? Okay. Haven't seen those. Hi, Fuji. Fuji loves this book. He loves it. He loves this book. Amazing Amanda. Owendra's only ever seen 2 movies and they were both Bollywood ones. Lols. Lol, 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 lol. There's some extremely cute kitty cats here, Amanda. Are you ready? Amanda! Ooh, can we please like the live so that maybe I could get 40 likes? 40 likes. 40 likes, maybe? 40? Oh, hi, babies. Amanda says hi. Hi. There we are. So I was trying to show the galaxy picture, but Fuji is on this book, because why not? I love kitties. So do we. You should definitely join the channel. Like, share, and subscribe. Oh, look at Fuji was giving a kiss to Baji. Let me move this paper towel bit. Fuji just gave a kiss to Baji, and look at who is over here. Who is this girl? Who? Who is this girl? I just subscribed. Thank you. Fuji needs attention. Yes, he does. He does. He's my precious Baba. He did bite me on camera earlier, though, which is totally fine. I love when he bites me. My precious child. Thank you, God. Look at you guys and your cool chat. Love it. Hurricane Ian was supposed to hit Tampa head on, and I lived outside Tampa. Oh, wow. No reading books while I'm on your book, mommy. Yeah. Fuji does believe in a lot of work-life balance. He's like, okay, if I'm sitting on the book, it means you're done. It means no more reading from the book, no more work today. We've been talking a lot, then I just left and came back, and yeah, kitty's low. Oh, nice. Amanda, I don't think I've seen you before. Nice to meet you. Belgium, indeed. Virginia, Washington State. Oh, wow. I want to visit Washington. I'm in Boston. Sometimes we say that I'm from Belgium too, but I'm in the Boston area. Nice to meet you, my friend from Washington. Nice to meet you. I want to go. I think I've briefly been in Seattle, but I haven't really explored a lot of Washington. So, nice to meet thyself, Amanda. Look at this guy. Look at this guy. You're such a cutie. Baji! Oh my god. Baji drank my milk. I'm like, what is that sound? I put some milk out for myself and Baji drank it. Oh my god. I want to visit Europe someday. England, Germany, Belgium, places like that. Nice. I cannot believe this. Baji, you drank my milk. Wow. That is a shame, I must say. Guess I'll pour myself another and actually keep an eye on it this time. Why, thank you, Baji, for helping me with the cleanup of this kitchen. Good night, Reese. Good night, everybody. Baji drank my milk. Unbelievable. I mean, it is believable. The Milky Way galaxy and the milk being had by Baji. All in a day's work. We talked about the Milky Way galaxy and now my milk has been drank by Baji. That's what we get. Milky Way galaxy and milk dranked by Baji. There, I can show you another picture. Here, you can look at NGC 7252, remnant of a galaxy merger. Right here. This is kind of hard. 1 second. It'll be upside down, but you can still see it. It'll be upside down, but you can still see it. NGC 7252, remnant of a galaxy merger. Right there. All right. Thank you so much, everybody.